All right, so now that we have a basic understanding of how DOP networks work, let's actually start our first real POP setup. And as you will see, this is a pretty long video because even in a simple first example, there are so many things we have to talk about. So let's start with the first scene, and we have an empty geometry here. And I will start with a simple sphere that I scale down a little bit, and I prefer a polygon and give it a little bit of subdivisions and then move the whole thing up, because this is where our particles will come from. So now let's fill a DOP network and let's connect the sphere in the first input because we will use it as a source. And when we're inside of the DOP net, we know that the main elements of any simulation are the solver. So we start with the POP solver, there it is, a POP object where our particles will live in. And then we have to get the particles from somewhere, so we create a POP source. There we go. And here's the first helpful trick. You don't actually have to create those yourself. We can delete the whole DOP-net because there's already a preset pre-built for us called a POP network, which is simply a DOP network already prepared with those three nodes. There's a merge in here that I usually delete because we don't need it. It's not, a super great shortcut because it's really just those three nodes and nothing more, but a little bit of a shortcut nonetheless. So let's start by using our sphere as a source. And the cool thing is that the POP source in a POP net is already set to use the first context geometry. In other words, our first input where our sphere from outside is in. Now, when we just press start, we can see, okay, there seems to be points generated, but they don't do anything. And first of all, they are currently created on the surface of whatever geometry I put in. Later on, we will see we can do other things. For example, we could create the points ourselves outside of the simulation, and sometimes we want that. But in our case, we're fine by just scattering onto a geometry that we put in. And like I said, we use currently the first context geometry, but if you want a specific path or maybe another input, then you can choose this here as well. So before we move on, let's actually make the particles do something. And usually the first thing you do in the world that we live in is we add a gravity. So we start right away with some kind of force. So just press tab and you will find the gravity force. And you can theoretically put them up here if you wanted. So if you would have multiple POP objects, which is actually possible, you could apply the gravity to those, or you apply them, if you put them down here, to everything. And this is usually where you put your gravity. In general, you can always tell where a node is supposed to be because of the colorization of the inputs and outputs. So here it's gray, so you can either put it here or there, but this one is purple, so probably it will not be expected here. And when we press start now, you can see, yay, our particles actually fall down and move. And again, keep in mind, and here I think this is pretty obvious, DOP networks do not work like SOP networks. So it's not a constant stream of data from the top to the bottom. It's more like a blueprint that defines our world. So in the center is our brain. It is influenced by gravity and the ground plane. And the particles that are used for all this live in the POP object and come from the POP source. So not really from top to bottom, more like, everything all at the same time. And this is important to keep in mind when working with simulations. And that's also the reason why I never changed something like a display flag, but my output flag always stayed on the output. We talked about this. I just wanted to repeat it again because it's so important. So let's actually add a bit more to our setup here. And that is, let's now add a ground plane, because currently they fall just down and they keep falling, which is something we have to talk about later on because we don't want that. But for now, let's make them collide with something. And one very common thing is a ground. And sure, you could actually create a geometry that represents the ground, and sometimes you have to do that. But because a ground is so common, we actually in our simulation world have a ground plane. And the weird thing is, as you can see here, there is no input at the top. So we have to somehow bring this into our setup. We can't just, snap it in like our gravity. We have to do it in another way. And that is actually, like we already know from SOPs, a merge. But be careful here. The merge works differently to the merge on the SOP level, because if we press start now and see what happens, you can see that the points actually fall down. If you press W, you can see that even clearer. Currently, the ground plane doesn't do anything. Why is that? Well, unfortunately, for some reason, the merge node has a certain order. And you can see that actually when you select it, it says left inputs affect right inputs. So sure, we could change the order of the input. By the way, you can do this here in this list. So when you press on the ground plane arrow, then the ground plane comes before the rest and then the collision works. But honestly, nobody does it that way because it's way too much work. Instead, what we just do is we change the settings to mutual, and then the merge will always work in any order that you put the stuff together. And trust me, from my experience, that is not dangerous in any way. Everybody does that, basically. So if we run this now, we can see there is a collision. And now I think is a good time actually to quickly point something out that we already talked about, and that is your timeline caching down here. Because everything that is already simulated is cached out in your RAM so that you can basically reuse it. This is, by the way, one of the reasons why you should always have your hardware monitor or task manager open to see what your RAM is doing right now, because this can eat up your RAM quite quickly. So anyway, what you will notice if I quickly turn off my ground plane again, you can see that before the timeline cache was blue and now it's orange. And of course, that means that the timeline is telling me, well, listen, what you're looking at right now after you changed your setup is not the correct result. So in a case like that, you always just have to rewind and start play again. And this is just the way simulations work. You constantly rewind when you change something and simulate it again. At this point, we should be aware of this. I just wanted to make sure that we are all on the same page. It's a bit boring right now because the collision kind of bounces back instantly, as you can kind of see here. So let's make this a bit more interesting. Before we talk about other things, let's actually give our points a start velocity, some kind of direction. And later on, we will actually see this is something we could already define outside of our simulation by actually defining a start velocity on our sphere. But to start simple, we can also set this in the pop source directly. And the first thing we should actually talk about is in the birth tab, because here we can control very important things like the amount of particles we create. But let's go further and start first with attributes, because here we can set the start attributes for the points that are created by our pop source. And one very important one is velocity. By default, it's set up so that the inherited velocity is set to 1, which just means if our sphere would already have a velocity, our points would get the same. But right now our sphere is just static, so that doesn't help us. So let's change this to set initial velocity, and now we can actually set our own velocity here the way we want. Now we have two inputs, the main velocity defined by x, y, and z, and a variance. For now, let's turn off the variance so that we understand the whole thing better. And let's set a direction that is, 45 degrees in this direction. So what we have to do, and unfortunately my head is in the way, so here you can see, we need to find a vector that defines this direction, which is y and x and no z, because z is towards us. This should be basic math for you, basic vector math. If that doesn't ring a bell to you, maybe read up how vectors work again. You probably have heard this in school. So here, for the first time ever, probably we'd actually need that knowledge. So if we've done everything right, we can see that, they kind of fly in this direction a little bit, our points, but it's not strong enough. And that's another thing about vectors. We can just make them longer. So as long as the relationship between x, y, and z stays the same, we keep the direction, but we can actually increase the numbers. So as long as x and y are the same, so let's say 4 and 4, then the direction will not have changed. But now the whole thing is 4 times faster, as we can see here. And now we have a proper arc that flies through space. Now it is actually quite helpful to understand how to build a vector like this yourself, but I have good news. SciEffects actually built in a technique to make this whole thing a bit more intuitive. And that is when you take any kind of vector parameter, it doesn't really matter, you can take the parameter by clicking on it and then just dragging it into the viewport and activate the pivot handle in this case. Now, nothing seems to have happened, but what we got now is this here. And this shows us basically the end of our vector. So this can be helpful, and let's actually rewind to see this better, to define in which direction we want to shoot the whole thing. You can more intuitively this way change what you want. But let's set it back to 440. And let's talk about the next thing, and that is the variance. What that means is when I set them all to 1, that the velocity for x will be 4 plus minus 1. So that's important. It's not just added on top of it, but it's a variance in both directions. So that means the slowest particle that will be created will have a velocity in x of 3, and the fastest a velocity in x of 5. Same for y, because it's 4 plus minus 1. Now, what does it mean when we do this? When we press start, we can actually see the result. That's just a spread. So it's easy to remember the variance is just a spread. And we can define in which direction we want to have the spread as well if we want. So for example, let's only add spread for y actually. And then we will see there's only a spread upwards and downwards, but when we look from the side, there's no spread in the z direction. So you can really control the spread quite specifically that way. But in our case, we probably want this on all directions. And of course, the higher the variance, the higher the spread. So let's set it to 3, and then you will see the spread is much higher, probably a bit too high for our case. So this is a very nice way of adding, a bit more believability to your setup. In this case, I would probably go with something like 0.5, because depending on the main velocity, that seems to make a lot of sense to me. For now, we will set it back though, because if you turn it on, you will lose a problem that I want to talk about. So let's keep it at 0 for now to actually be able to see the problem a bit more clearly. Now, the thing is, before we move on and talk about why this here happens, which is really ugly, and unfortunately something that only came in with Houdini 19.5, let's first talk about other attributes than velocity. Because not only can we control here under attributes the velocity, which is the most important attribute to be fair in POPs, we can also control what attributes will be inherited from our sphere from outside on top. And this is something we can actually do right now to make this look a little bit less boring. For example, because any attribute we set on the sphere outside here, our points will inherit. And one example could be color. So let's use not just a color node, but an attribute adjust color node, because as we've learned, this one is more like an advanced version of the whole thing and gives us more options. And one of those options is that we can set a color based on the bounding box. And the idea here is that I want to give it some kind of, color palette based on, the whole size of the sphere. Currently it goes from our position left to right because we set it to X, but if I change it to Y, it goes from the bottom to the top. And let's change the color palette to, let's say, maybe plasma, because I just like it. And the cool thing is this attribute is now created on the points of our sphere, and this attribute will then be inherited by our particle simulation. So if we just look through our PopNet and press run, we can see now, yay, we have colorful points. Not amazing, but at least a bit more interesting than just black particles. So unfortunately, I would actually talk about other things, but we have to talk about the elephant in the room. Why is it not behaving here as we would expect? We would expect the points to make an arc and then, bounce off here, but they don't. Why is that? Because for some reason, side effects in their wisdom decided to change the defaults that they had for 20 years with Houdini 19.5. And we will actually talk about what they changed here in a later video. But for now, let's go into the pop object, because what they changed are the physical properties of those points, namely the friction. I only wanted to talk about this later on, but now we have to talk about this. But when you select the pop object under physical, you will find the properties of our points. And they are very bouncy and at the same time very frictionless, which is kind of weird. And in the past, the friction was set to 0, and I would ask you to do the same, simply because then our first setup is a bit easier to understand. And there you go, now we have some bounciness going on. We will talk about this more later on, but here now we already have seen the particles have properties that we can change, for example, bounciness and friction. But let's move on and go back to our particle source. And now that we know that we can set certain directions, let's also talk about the amount of points that we have here. So in the birth tab, this is where we set probably the most important stuff, like the amount of points we create here. And here you can already see there's a constant birth rate of 5,000. So this is pretty straightforward. If you want to have 3 times more particles, well, then just be turn it to 15,000, and there you have it. Now we have 3 times more points than before. But the question is, why is it only the 4th element here or parameter that we have to change? What's with those 3? Well, unlike what you might think, 15,000 doesn't mean that our pop source will emit 15,000 points every frame. It will actually emit 50,000 particles every second. So if we go back to the first frame and middle click somewhere, and it doesn't matter where, because it's all one big world that we live in, we can see it's 625 points that we have right now in our scene. And based on our settings in the global animation options on the lower left, we can see that we have 24 frames per second right now. So let's go to frame 24, which is exactly 1 second. And there we have it now, exactly 15,000 points. Sometimes we have 2 or 3 more or less, but this time we have exactly 15,000. So this is per second. Now, most of the time that makes the most sense because we don't think in let's call it volume of things in terms of what happens in a single moment in time. We talk about volume in terms of a certain time that we can perceive, like a second. This can be helpful, for example, for the amount of water that comes out of a pipe. It's a very natural way of thinking about the amount of stuff. But that's not always helpful, and this is why there is an impulse count. Because sometimes, and a good example for this is an explosion, we need to actually know what happens at one particular moment in time, like an explosion. So for this, we have an impulse count. So let's set the constant birth rate back to 0 and set our impulse count to, let's say, 300 and rewind. And on the first frame, you can see we have now exactly 300 points. And on the next frame, we have, surprise, 600 points and so on. So we can decide what kind of metric we use per second or per frame. Another advantage of using per second, by the way, is when we change the frame rate. So later on we can, as we will see later on, we can increase the basically precision of our simulation by increasing the amount of calculations that happen. And we can go higher than just calculating it for every frame. We can actually calculate twice between 2 frames or 3 times and so on. And that is called substeps. We already briefly talked about this. And if you would change the substeps, and it would not be based on seconds but on frames, then you would always have to adjust those numbers here. But since it's per second, it doesn't actually matter how many frames are in that second, it will automatically be calculated correctly. And by the way, you can, if you wanted, mix the two as well. It doesn't usually make any sense, but you can do that if you want. So it's not mutually exclusive or something, but usually you stick with one of the two. So for now, we stick with the constant birth rate, as you might have guessed, but later on we will see a case where we need the impulse count. Spoiler alert, fireworks. So next question is, why do we have constant activation and impulse activation? As the name suggests, what this means is you can activate each of the ways of emitting points. So if I don't want to emit anything, I could keep the 15,000 and just set the constant activation to 0, and then nothing will be emitted because this is a switch, an on-off switch. By the way, it's not a multiplier, so if I set it to 0.5, that's the same as 1. I don't get half the amount of points or something. It's really a switch. And the same is true for the impulse activation. Now the big question is, if it's really just on or off, why is it a parameter like that? Why can you dial it up and down? And the reason is kind of weird. This kind of inputs are much better usable for expressions. So as we've seen before, you can actually write in, for example, something like, if the current frame is higher than 20, then the result should be 1. And this is why we have an input parameter here and not something like a checkbox or something, because it's very common that you control your simulation this way. So for example, in this case, we set it that be only after the frame 20, the 15,000 per second will come out of our sphere. And this is exactly what happens. Boom. And this way we can control much better how our simulation should behave. So this is the main reason. We will not do this now, so let's delete this again with right-click, delete channels, or how I do it with Control-Shift left mouse button. But just keep that in mind, that's why those are number parameters, not just switches. All right, so that's great. So now we can control the amount of particles. So let's now talk about something you probably already noticed, and that is this annoying stuttering here. So that you have those, in the beginning it looks fine, but then it starts to get those weird liney things. Let's talk about this in the next video, because I want to split this up in 2 videos to make it easier to digest. But before we do that, we will actually look at this problem in a different setup. We will turn back under attributes our velocity to 0. And we will also delete our ground plane, or deactivate it at least. And now I can see our points just fall down like I expected without a ground plane. And in the next video, we'll talk about this horrible sphere problem here that we can see here very clearly. Why the hell does it happen and what can we do about it? So for now, I hope this video was helpful. Thanks very much and see you later. Cheers.